A lot of data, you might actually try to do some histogram KNN based method of estimating your density, but you would really need lots and lots of data sort of everywhere that you're likely to get a point, because you need the densities pretty much everywhere you're likely to get a data point. And in some sense, the whole point of generative models is to be able to use a modest amount of data. So the reason to use the parameterized thing is that you don't need a lot of data, okay? And it allows you to generate a model that you can use for each category. So in summary about generative models, there are some good things about it, right? It's pure probability, right? Very, very clean probabilistic thing. In fact, it's been known for a very long time, which should give you a hint that it's not going to be the most powerful method used, because it comes from a time when computers were non-existent or scarce, and we had to use a lot of mathematical reasoning, pure mathematics, in order to do the work. But it is it says here, firm probabilistic grounding. It allows you to use your priors. So if you have priors, maybe your context gives you a prior. I know that I'm in a bedroom, so the probability of seeing a lamp is a lot higher than if I'm in a garage, okay? That kind of thing. So I can have a prior built into it. One that's in yellow here, actually there's two of them that are yellow because I think they actually are important. One is that because you're doing this parametric modeling of continuous functions, you can actually get away with using a pretty small amount of data compared to other methods we're going to look at later, the discriminative methods. So that's one. And the second good thing about it is your models are about each category and just about the category. So when you tell me about some new category, I just have to learn a model for that category. I don't have to play with this model. Whereas if I'm trying to learn how to distinguish between an A and a B and an A and a C, now you tell me about D's, I have to worry about A's versus D's as well. So when you add in new categories and you're trying to discriminate, you often have to worry about a lot of different categories. In the generative model, I just build a model for that new category. There are some other advantages of generative models that we haven't talked about. You can use unlabeled data in interesting ways. You can also use it to generate data, right? So if I say something is distributed over Gaussian, I can actually make more examples, and there are times when that's useful. So that would be all the good news. What always follows the good news is the not so good news. So where did you get those priors? Okay, so again, you go to Greece, you go to the Sears prior store. The sensitivity of the priors really matters, and the priors can be affected by things like context. There's this other thing that's also kind of annoying. I'm modeling skin, and I've got not skin. Well, skin, you might say, is a plausible model. Not skin? Modeling not skin is kind of a weird thing, right? What I really want to do is model sort of the boundary between all the stuff that's skin and everything else that's out there. And by the way, a lot of the stuff that's out there doesn't look anything like skin at all, so that stuff is easy. What I really need to worry about are the things that are kind of like skin but aren't. And in fact, that's the next example. It says, the example hard cases aren't special, and they should be, right? So if I'm trying to recognize, rattlesnakes in the brush, I don't have to worry about what Maseratis look like. I do have to worry about the difference between what rattlesnakes look like and maybe different kinds of grass, because there's a tight similarity between them. So this idea that modeling the hard cases is really what's important. In fact, I think that's what's most important about discriminative learning. And then the last thing is, if you have lots and lots and lots and lots and lots of data, it doesn't really help. If I'm modeling my world as a sort of a single distribution, once I have enough data, I can fit some nice mixture of Gaussians, I'm done. It's not helping me in comparing against other elements. So it's not really leveraging having large data. So those are the downsides of generative models. So next time, we're going to do, we're not going to give up generative models yet. We're going to show you a really cool way of building a sort of a low-dimensional generative model called principal component analysis. It was first done, not first, but became popular when done for face recognition, and that's a form of a generative model, but most important, you'll just learn about principal components, which is used a lot in computer vision for all sorts of things. And after we do that, we're going to move to this other set of methods which are discriminative, where instead of modeling the categories themselves, instead we learn about the boundaries between the categories. And that we'll continue to do as we talk more about recognition. Welcome back to computer vision. Today we're going to be learning about a technique that is important in general, but we sort of slid it here, and we're talking about recognition under the generative model description. So last time we introduced, which I hope for you was last time, certainly for me it was last time. They say you never forget your first time. Me, I can barely remember the last time. Last time we introduced generative models for classification, and there were a couple of points about generative models. Megan's still giggling in the back there. One of the points was that in generative models, you build a new model for every new object category. And you don't really think too much about the other objects that you know about, and you just you build a description, and when new things come in, you see how likely is the new thing for each of the description, each of the models that you have. But there was another point, and that was perhaps a little more subtle because it was kind of flew by, and that is that generative models work best in lower dimensional spaces. And what I mean by that is since we're going to build these probabilistic descriptions, usually some sort of probability density function, it's only plausible to estimate those when you've got a modest number of dimensions. If you have a very high number of dimensions, or even just a moderate number of dimensions, to estimate a real probability density requires lots and lots and lots of data. So today what we're going to do is we're going to learn about one of the most common and perhaps, I don't want to call it important, but just everybody would expect that you would understand it, method of dimensionality reduction, which is referred to as principal component analysis. You may have seen this in other signal stuff or maybe in linear algebra, but it became pretty significant in computer vision because of a particular piece of work that I'll tell you about, and because of that it gets used all the time. Principal components. So fundamentally, principal components are about the directions. The component is really a direction in a feature space along which the points that you care about in that space have the greatest variation or variance. We'll make all of this more formal in a minute. So the first, it says PC here, first principal component is the direction of maximum variance. Now, a quick word of warning. You can see here I've got this little symbol here that indicates that's where the mean of the points is. Principal components is mathematically defined about the origin. So what we typically do is we talk about moving all the points to have their mean at the origin, but then we forget that it's doing that. We have to do it in the math, and we would draw something like this and say, you see this direction, that's the first principal component of those points. It's the direction of maximum variance. They're not around the origin here, so we have to shift it actually before we do the computation, but when we think about it, we're only talking about with respect to the mean. And the subsequent principal components are perpendicular or orthogonal to the previous ones and describe the next greatest amount of variance. Now in 2 dimensions we're sort of done, right? So we say, well, that's the first one, well, the next one's got to be there because there's only 2 dimensions, so it's got to go that direction. But if I was in 3 dimensions, I would have my first dimension, and then everything would be along there, so I could remove that, collapse it down to a plane. I'd say, in that plane, what's the maximum variation? That would be my second one, and then I would have the third one that would be left. This notion of maximum variance should strike a little bit of recognition in your mind about the notion of fitting a line. You remember we did line fitting? Okay. In fact, we came up with this equation of saying we're going to measure the error that's essentially just the perpendicular error of the points to this line. And the equation of the line that we had there was ax plus by minus d equals 0. Or it could be plus d. It doesn't matter. The idea is that a and b was the normal with respect to the line, and in fact that's what that says right there. And when I take the dot product of x and y on that, it's supposed to be a distance d away, and that's what this equation says. All right, so that was when we were trying to do a least squares fit. So then we did this quick operation. We took the derivative with respect to the d, came up with this formula for the d in terms of the average x, the average y. We plugged that in. Substitute d equal ax bar by bar. We get this new error function e, just having substituted, and we wrote it this way, okay? And this is where b is this matrix here. And you can see it's just the x's and y's in rows with the means subtracted, okay? So what we want to do is we want to minimize that quantity, the magnitude of b times n, where n is going to be the normal ab that we're going to solve for. And we said last time that what we want to do is we want to minimize bn squared. But remember, since the normal has to be a unit normal, we say subject to n equal 1. Now, what might be not so obvious, because we didn't mention exactly last time, is that this distance, these square distances, this is going to be the axis of least, what's called the axis of least inertia, right? Remind you from your physics, if I've got an axis, then the inertia of the whole thing is proportional to the sum of all the points, the square distance from those points to the axis. So the line fitting here in 2D is an axis of least inertia. And like I said, this should sound familiar to you. And remember we did this, we looked at several ways of doing this. We had those, in fact, back when we did calibration, we said, well, we have this AM, because we were doing M matrix for the calibration. We said let the norm of that, well, we want to make it as small as possible, subject to M equal to 1. And remember, we were doing this thing with eigenvalues and eigenvectors. So it shouldn't surprise you that we're going to be revisiting eigenvalues and eigenvectors. Let me give you another algebraic interpretation of principal components, and eventually this will just get us to our formulas. Here we have our point P, and let's suppose we have some origin. If we want to minimize the square of the distance from the point to a line, we want to find the line that minimizes that square, well, you remember Pythagorean's theorem? Of course you do, right? It's that the sum of the squares of the two legs of a right triangle are equal to the square of the hypotenuse. If we want to minimize the square distance of the point to that line, we can say the same thing as maximizing the projection of that point on the line. That's what this value is here, right? X transpose P. X is some unit vector through the origin, and if we project P onto it, that's going to be the vector, and you want to maximize that length. So minimizing the sum of the squares of the distance to the line is the same thing as maximizing the sum of the squares of the projections on that line. A way of writing that is we want to sum up all the squares, and this is just a little bit of a matrix manipulation trick, right? If I wrote my points down here, right, of x1, y1, or an x2, y2, and if this was my line, so maybe it's AB, right? If I multiply x transpose b transpose, so now this is b, xy, xy, bx, all right? If you multiply that all through, what you'll realize is it's exactly that value, okay? It's the sum over all the points of that square of the magnitude, all right? So what that means is algebraically, this maximizing the projected distance can be written like this, right? So our goal is to maximize x transpose bx, but we've got a constraint, right? X is a unit vector. So that means that x transpose x has to equal 1. So what we have to do is we have to maximize this subject to a constraint. All right, so that's what this says here, and I wrote it as M, maximize equal to x transpose mx, where M is b transpose b, so we just have a single matrix. Now, I'm not going to tell you a lot about this method, but I am going to introduce this quick notion of what's called Lagrange multipliers. Here is E, and here's E prime. And you notice that what we added to E prime is this term, lambda times 1 minus x transpose x. So Megan, if everything is solved correctly, 1 minus x transpose x should be what?
0?
Whoa! Yes, 0. So when this thing is solved correctly, it doesn't matter what this lambda is, right? Because it will add 0 to the term. That, in a very hand-wavy way, that is the method of Lagrange multipliers. It says, I'm going to put in a term multiplied by a lambda that will be 0 at the correct solution, and then you solve everything and you've satisfied your Lagrange multiplier method. It turns out in our case it's even easier. So that's our E prime. So what we do now is we take the derivative of that new error function, E prime, with respect to x, and we get this, 2mx plus 2 lambda x is the derivative. And now, in order to minimize this, we set this equal to what, Megan?
0.
0, very good. We actually rehearsed that one this time. And so when you do that, you get this very simple equation that says mx equals lambda x, all right? Forget the positive or negative, it doesn't matter because lambda can go in either direction, all right? So that's a very special x, right? So when I multiply x by a matrix M, if I get back a linear multiplier, in this case lambda, of x, that means x is an eigenvector of the matrix M. So that means that X is going to be an eigenvector of this B transpose B.